I sent this document around to everybody, and hopefully you had a chance to look at it. I'm going to try to do this with the screen up so that I can write on my diagram. Loud out here. All right. So basically, the place where I managed to trip myself up was the same thing that trips everybody up, undergraduates included, and that is getting the signs on the arrows wrong. And it turns out if you can get that right, you can get everything right. And I think what makes it especially nuanced is that for the mutual inductor case, it sort of works a little bit backwards from the transformer case. So in order to get everything to square up for the mutual inductor case, you want the you have your voltages, your dots on the inductors to indicate which way they're pointed, and you want it to find positive current flowing into the dots. Okay, you don't have to do it that way. It just makes everything work out positive. Okay, so if you wind up with a problem where the arrows are pointed the other way, you can just reverse them, and at the end of the problem, reverse your current. Just make your currents negative, and it should all work out. All right, but if you do it in this way, it works out pretty cleanly that the voltage across this node V1. Remember, for an inductor, it's V. What's the voltage for an inductor? LD IDT, or in the phasor space, it's j omega L. Okay, so in this case, you get j omega L1. So it's well, as I say here, it's I1 times j omega L1, plus you get whatever I2 is. That's your I2 goes through your mutual inductance, and you pick up a mutual inductance term. Okay? And then it goes the same for the other one. So just to set up the equations for the, so this is the quiz you had. I don't know if you can read that too well. But white chalk, black sweater. All-time bad combinations. All right, so as you can see here, let's see, that's 1J, that's 1, that's 1J, that's 2J, that's 1, and then this is VL. Right, so if I'm presented with this problem, the first thing that I want to do is to draw the current arrows. Okay, if I draw the current arrows, the whole problem gets like a bazillion times easier, right? So I'm going to draw, as I've just indicated in the previous problem, I'm not obliged to do this, but it just gets a lot easier if I draw my currents in this direction, both pointing into the dots. Okay, and if I do that, everything just adds up. So now I'm going to write KCL KVL, sorry, for both loops. So let's start on the left-hand side, okay? So I'm going to start here at 0. So now I'm going to go up. What happens if I go up? What happens to my voltage? It goes up by 12 angle 0. So I'm going to go up by 12 angle 0. Now I've got a voltage drop across this resistor. A voltage drop or a voltage increase? Drop, right? Because I'm going in the direction of the current arrow, it's defined as a drop. If in fact the voltage is actually increasing, that's okay. This will still correctly predict that. You'll just get you'll wind up with a negative value for the current, so it'll work out. But we're going to model this as a voltage drop. So that's going to be minus I1 times the resistance, which is 1 ohm. And now where does that leave me? Right, so now I've got to get back home. Okay, so basically now I'm left with V1. Right, V1 is the voltage at the mutual inductor. Right, and as you've just learned, the voltage at the mutual inductor isn't just a voltage drop from, we know there's going to be a I1 j omega, actually it's not j omega, it's just whatever the impedance of the inductor. The impedance in the inductor is just J. Right? It's not just an impedance drop from this inductor, but I'm also going to pick up an impedance drop from the mutual inductance. So that's another drop of I2, and the mutual inductance is 1J. Okay, and now my loop is complete, so I'm back to where I started. So that all equals 0. Okay? How do I do the loop on the right side? Same thing, right? Do you want to go clockwise or counterclockwise? Should we go this way or that way? Does it matter?
Not really.
Not really. Just no. It does not matter, right? It doesn't make a lick of difference which way you start. So let's start here and go this way. Okay, so I'm going to go over the 1 ohm resistor. Is that a voltage drop or a voltage increase? Did I go in the direction of I2 or against the direction of I2? In the direction, so that's a drop. Always a drop, right? Always, always, always. If you define positive current to be in that direction, then you go down in voltage if you follow the arrow on a passive component. So it's going to be a voltage drop of I2 times 1 ohm. What about here? It's a drop of also I2 times 1 ohm. Okay. And now we're at the inductor and the mutual inductor, which are also going to give me both drops. So this mutual inductor is, the actual inductor that's there is going to give me I2 times the impedance of the L2 inductor, which is 2J. And then I'm also going to pick up a mutual inductance drop, which is going to be the opposite current, I1, times the mutual inductance, 1J. And now I'm back at 0. My loop is complete. Okay? And now I've just got a mess, right? But it's a system of 2 equations and 2 unknowns. The only thing that's a little bit unsavory about it is that it's all your coefficients are complex. But still, it's a system of 2 equations and 2 unknowns, right? We should be able to manage that. So as indicated in the handout that you got, whatever it takes, I don't care if you've got some sort of special widget on your calculator that will solve it. I don't care if you have to solve it by hand and it fills up 8 pages of paper. Like, I consider a 2x2 system of complex equations to be a reasonable thing to put on a quiz or a test. Definitely a test. Definitely a final. Okay, it's just, however you need to solve it, solve it. Yes, sir?
Can you put like 1 plus j as a value in a matrix on MATLAB?
Absolutely.
I tried it and I was just getting some discrepancies in the numbers.
Let's try it. You want to give it a shot? I mean, it's actually not that bad, right?
Yeah.
So the only thing you need to do in order to do that in MATLAB, and this may be, I don't know if this is what tripped you up, but you've just got to organize. You've got to collect like terms, right? Okay. So if you take the first equation and collect like terms, you've got I1 times what? 1 plus j plus I2 times j, and that's going to equal my constant of 12 angle 0. And for my second equation, I've got I1 times j plus I2 times 2 plus 2j. And that's going to equal 0. So let's try it in MATLAB. Yeah?
What did you say? Did it matter before the direction of the current didn't matter?
Correct. I could have drawn this current to be clockwise. But if I did that, the mutual inductance, I would have had a bunch of minus signs to contend with in doing my mutual inductance. But it still would have worked out okay. Okay, so let's pull up MATLAB. Okay, so essentially what we're saying is, I'm typing right there in case you're trying to follow along. So my coefficient matrix is A equals 1 plus J, J, and then semicolon for a new row, and then it's J and 2 plus 2J. All right. And then my constant matrix is 12 angle 0 is just 12 and 0. And finally, I'm going to say I is A. Now this part often gets people. The right way to express this in MATLAB is your constant matrix, sorry, your coefficient matrix, backslash. That's the constant matrix. That's actually how you solve it in MATLAB. Yeah.
Full screen, I think.
Oh yeah. I'm sorry. There you go. Did that do the trick? Right. Okay. So coefficients, constants, and that's how you actually solve the that's actually how you do the system of equations in MATLAB. I mean, technically speaking, what you've got is matrix A unknowns equals B. So if you're doing a matrix calculation, another way of saying it is that X equals inverse of A times B. And you could actually solve it that way in MATLAB as well. You could say inverse of A times B. But this has some mathematical properties that are not very good. Like if you try to invert a matrix, a lot of the times you get this, unless the matrix is well defined, you get these singularities, and mathematically this doesn't always work. So this always works, yes?
Can you treat it as a 3 by 3 and then do reduced row echelon?
What would the third row be?
2 by 3.
Yes. Yeah, you could, right. You could do it with back substitution and like just a regular, like reducing the matrix. That would totally work. Right? Well, let's just start by making sure this works. Okay? So I'm going to do this. So what's my values of I? Display I. So there's my two values. So there's I1 and there's I2. So it's just expressing it in rectangular form. I can express it in polar form by taking the magnitude and the phase. So instead of displaying I can display the magnitude of I and the phase of I. Right, so there's magnitude and phase. And that's it. Once I know I2, my output voltage is negative I2 times the resistor. So you want to do it with a reduced, you want to like just reduce the matrix?
I treat it as a 2 by 3. So I just, instead of, I did 1 plus J, 12, J, 2 plus 2J, 0.
Yeah.
Like that whole matrix, I did reduced row. And my numbers were off. Just off. Like,
It's a heck of a method. It'll work. Actually, this should not be that bad, right? Because so you've got,
they were in the ballpark, but I felt like they were too far to be.
right, to be just like a rounding error or something. So listen, you've got 1 plus J, 12, and then you've got J, 2 plus J, 0. So what was the first thing you did?
I just put that in MATLAB as A, and then I did a reduced row echelon.
Oh, you actually had it. Oh, I thought you did it by hand.
No.
Oh. Let's investigate. Let's investigate your method. Okay. So your matrix looks like this. Okay, and then what was the command you did? RRE. Oh, I actually have to give it an output. Looks good to me. Right? Because according to, hold on, if I do my method, it's the same thing. User error. Tough break. Yeah, well, I'm happy to look at your code if you show me. You can even do it by hand. In this, was that?
Yeah, that one's not. I was doing the second one.
Right,
It's
right.
more complicated.
It's a lot more. Yeah. Use a computer. That's, that's not a cop out. That's what you're supposed to do. In fact, I think I've purposely given you problems that are so much of a pain in the butt to do by hand that I've hopefully adequately motivated you to like figure out how to do this on a computer. Because learning how to do this is less work than learning how to do it on a computer. That was my hope, anyway. All right, questions? All right, so real quickly, the inductor problem, which I screwed up, or not the inductor, the transformer problem. Again, I got it backwards. The key thing that I missed is that we had the equations right, but the equations only work for, this is sort of like the default configuration, and for that to work, I had the I2 current pointing left, you have to have the I2 current pointing right. If you make the I2 current point left, you basically just get a minus sign everywhere. And I didn't have that minus sign, therefore I was just getting not the right answer. But it turns out, if you just follow the exact same steps that we followed, but you reverse I2, everything else works out exactly perfectly. Right, so this is the example we did in the book. You've got I1 pointing in this direction. Again, we had I2 pointing to the left. If you simply define it to the right and follow your passive sign convention, all the equations work out. What do you think? Okay, again, I wound up with a system of complex equations. Right, I think in this case you can actually solve them by hand because you can just double one equation and add to the second one. But again, either way, it's a complex equation. Yes, sir?
So by default, the currents have to point clockwise for this kind of
In order to get these equations to work out without any minuses. I mean, so for example, let's say you decided to have I2 point to the left. Okay, so what would change in these equations? There'd be a minus sign here. Right? If you had I2 pointing to the left, you just pick up a minus sign here. And that's it. Right? But unless you put that minus sign in, you're not going to get the right answer. Right? Same thing. If you were to flip this voltage, you would have to negate one of these V's in order to account for the fact that you decided to flip the voltage. So sometimes in those problems, they try to be tricky. Like, instead of giving you the nice clean version, they mess with the arrows and stuff. Again, it's no big deal. You just start with the default version and then flip whatever currents or voltages you need in order to make the equations work out. I mean, personally, between you and me, I don't know. Well, I don't want to say I will or I won't do anything, but I enjoy, on an exam, for example, I don't enjoy, like, if someone screws up a problem just because they got the minus signs wrong on some, like, sneaky thing where the arrows were, that just annoys me because it's like I didn't really test to see whether or not you knew the material. I've just tested to see whether or not you knew the plus was, you noticed the plus was upside down, which I think is kind of a pointless exercise, but that's just me. But anyway, that's the default. If you do it this way, everything works out positives. You know, if the picture comes out with other stuff, you know, apply accordingly. All right? It ain't too bad. Once you get that straight, I mean, like the whole chapter's a piece of cake. I shouldn't say a piece of cake. I don't mean to sound dismissive. But it gets a lot simpler if you get your damn diagram straight. Okay. Questions? Okay, so here's the deal. We are going to have the rest of today, Friday and Monday, to talk about three-phase circuits. And then Wednesday we'll do just kind of shoot the bull. If you have questions, you want to talk about the exam, you want to work problems from the book, whatever. Your exam is going to be, again, you got to know everything, but your exam will definitely be focused on where is it? Chapter 9, which is power. Chapter 10, which is magnetically coupled networks. And what we're going to start today, which is polyphase circuits. We've actually covered a decent amount of Chapter 12. Chapter 12 is like Bode plots. And if you poke through Chapter 12, this is all stuff that we've talked about. We didn't talk about like every last bit of it, but we've definitely talked about transfer functions and so on in some detail. So, but anyway, like I said, your exam will mostly be 9, 10, and 11. So I want to make sure that we get at least 3 lectures on Chapter 11. All right? Okay, so I think I'm actually going to go without the computer for the time being. So let's see how I do that. Think we'll get another fire alarm? Okay, so somewhere along the line, some of you may have been advised to use your Temple engineering degrees to get into the power field. And I'm no expert, but from what I understand from people, that's actually really good advice. Turns out that the people that run your power grids all across the country are all like 65 years old and looking to retire. And no one's gotten into the field in the last 30 years. So apparently, if you want job security, you should learn how to work. That's apparently a great field to go into. And that's how we get to polyphase circuits, because three-phase circuits are, they actually underpin a lot of power delivery. Okay, so the main application is power generation and delivery. All right, and it turns out that there's certain efficiencies that can be generated by creating power and delivering power in this way. So essentially, the way it works is instead of having one voltage source deliver your power, we're going to have 3 voltage sources delivering your power. So, and I'm just going to use my notes so I don't get the signs wrong. Once bitten, twice shy. So the basic diagram kind of works like this. Does anybody know why we transmit AC power instead of DC power? Yeah, it's more efficient and it goes longer distances without losses. Exactly. So the question now becomes, what's the most efficient way of transmitting AC power? Okay. So let me just get my notation here. So we're going to call this A, B, C, and N for neutral. Okay. So this is like a classic 3-phase circuit. Yes, sir.
Am I right when I say that it goes longer distances because most of it is done like around the wire instead of like through the wire where it's resistance? Because of the field when it's AC.
Ooh, I don't think so. I learned this once upon a time, and it was a long time ago. There is something called the transmission line equations, and I think it has. Oh, rats. Let me look that up because it is actually really interesting, and I remember learning it once upon a time and thinking, man, that is pretty cool, and then promptly forgot it. I was an undergrad too. I know how it works. If I can find a pen, I'll even make a note of it. Where's my pen? I think one of my kids took it. Anyway, I'll make a note about the power line, about the transmission line equations. I think it has more to do with the impedance of like driving a very, very long wire. I don't think you can really talk about like the charge moving on the outside or the inside of the actual conductor, but I'll get back to you. That's an interesting question. Okay, so essentially the way we're going to do this is we're going to put a cosine. We're going to generate an AC signal, right? So it's going to be a cosine voltage on each of my sources, but they're going to be out of phase. So for example, we're going to say that the voltage between the A phase and neutral. So you could think of it as some cosine. All right. So if that's the case, so I want to have three. I want to have three equally phased sources. So if a full way around a circle is 360 degrees, and I want them equally spaced, what's going to be the spacing between my two phases? Between each of my phases? 120 degrees, right. So the second phase is going to be, the B phase is going to be lagging the A phase by 120 degrees. And then the C phase is going to be, you're not going to believe this, each one lags the previous one by 120 degrees, right? So if this is the case, this will be what? Minus 240. And did you ever think that minus 240 is the same thing as positive 120? Isn't that nutty? Right? If you go, I'll show you what I do in my signals class. I think I've done it here before. Which way is 0? This way is 0. Okay. So minus 120 gets you to about here, right? Because there's minus 90. There's minus 120. So now let's go another minus 120. So minus 120 gets you to about, another minus 120 gets you that far. And that's actually the same as positive 120. Right? A less ridiculous way of doing it would be to notice that if you add 360 degrees to that, you get plus 120. So basically what we wind up with is you can just express it as a phasor even, right? You can just say you have Vm angle 0, Vm angle minus 120, and Vm angle either minus 240 or angle plus 120. Right? It all works the same way. Okay? And in a second, you'll see why we do this.
It is not the same as 60.
Is what the same as 60? 120?
240 is subtract from
Minus 2. No, minus 240 and 120 are the same. Right? If you have, let's see, here's minus 90. Here's minus 180. So if I do a 30 degrees here, that becomes minus, this becomes minus 120. And now if I go another 120 back, so let's see how I get to 120. That's 60 degrees. And then I'm going to go another 60 degrees. So now this, from here to here, is another 120 degrees. All right, 120 degrees. Well, if this is 100, from here to here is 120 degrees, from here to here is 90 plus 30, 120. So that's the equal spacing. So 60 is not in this yet, although we'll get to 60 in a little bit, I think. Again, I haven't specified the frequency even, right? We're just talking about phases. So the first advantage of this is that suppose we have what we call a load balance situation. So if it's load balanced, then each of the three phases, so you have this, in this case you have the same impedance on each load. Sorry, same impedance on each, same impedance on each phase. All right. So suppose whatever that impedance is, IA. So how could I write? What's an expression I could write for knowing what you know? If I put some load on A, how could I write the current that goes into that load? It's going to have some magnitude. It's going to be a cosine, square wave. It's going to be a cosine. What frequency? Omega t. Is that it? Will it be in... What's that?
Yes. shift.
Plus a phase shift, right? Because what if your load isn't a resistor, right? If your load is a resistor, this is it. But if your load is an inductor or capacitor or some combination thereof, then your current will lag or lead your input, right? They'll be out of phase. That's like one of the big things that we've been learning about all semester. So, minus some phase shift. All right, what's your what's going to be your B current? Again, assuming everything is load balanced. Almost the same thing. If it's the same voltage going into the same magnitude load.
You have to include the additional angle?
Yeah, but you have to include the additional angle. Exactly. So it's Im cosine of omega t minus the phase shift that comes from the load minus the 120 that comes from being out of phase, right? That comes from the phase alteration. And then I'm just going to write this out just to say that I wrote it out. We're going to get the same exact thing for the C current. Now, first lesson and why this is actually useful. Am I running into the glare problem? Like, is there a dead space of the board I shouldn't use? We have this problem. If I write here, can you see it? No, you can see it. No? Not so good. How about here? Okay. I won't use that part then. Erase my smiley face. Okay, so, right. So, let's talk about power. Instantaneous, what's going to be, so I've connected the same load to each of my three sources. So what's my how can I write an expression for my instantaneous power for the whole system?
Just the equation?
Yeah, voltage times current, right? So I could just take, so again, I'm assuming that each of these is driving an identical load. Whatever that load is, each of those three is driving an identical load. I didn't really want to draw it because we're going to get into, we'll draw loads in a minute, and there's different ways of expressing loads. But essentially, and I'm not going to, the book actually writes all these out, but essentially you're going to take the A voltage times the A current, the B voltage times the B current, and the C voltage times the C current. And the craziest thing happens. Because all your currents are out of phase, but they're out of phase by just the right amount, when you add them together, like three trig identities come into play. What happens? What's your instantaneous power for the whole system? Does it vary as a function of time? It doesn't. It's constant. Isn't that cool? Right? So that's kind of the first upshot of this. If you calculate, we didn't take an average power, right? Remember, we solved this problem in the power chapter. We solved this problem of time-varying power by taking an average power. But here we didn't have to do it. If we just multiply all those expressions together and add them, turns out like all the time-varying terms cancel each other out, and you wind up with a constant power. Yes, sir?
Guessing that's supposed to be C, the bottom?
This? That's a 2.
I.
I see.
For the third term.
Yeah, see.
You vote I.
Ah, yeah. I see. Yeah, you knew that. That's good. Okay. So that's actually pretty handy. And you can try this in MATLAB. Like, it's not that hard. You can generate the 3 voltage sources. You can generate the 3 current sources multiply and add, and you'll get something that's always constant, no matter what your phase is, as long as the phase between them is 0, 120, and 240. Yes, sir.
Why over 2?
What's that?
Why over 2? Is that within the derivation?
Yeah, it's within the derivation. It just works out. There's a 1/2 factor that pops up. It's like 3 trig identities that all hammer down at once, and that's what you're left with. But the point is it's constant. Right? I would focus more on the fact that it doesn't change. So if you're delivering power in a system like this, that's sort of the first cool thing about it, is that the total power that's being delivered to the load at any given point in time doesn't change, right? So it's like a constant power generator, even though you're delivering power using an AC source. So that's kind of trippy. It's kind of like you beat the system. That doesn't happen very often. Okay, so let's look at loads now. So we've got a three-phase power. Now we're going to look at how to connect up a load to this. Did you guys learn about Y and delta when you took Circuits 1? Yeah? No? Not a rousing answer. I'm going to guess not really is like sort of the answer. Not really. Okay. So basically there's 3 ways to work this. So let's talk about applying a load now. Come on, handwriting. Okay, so when we apply a load, so again, we've got from the supply, we've got A, B, C, and neutral. Okay, and we want to apply a phase balance load. So it turns out that we can do this in one of 2 ways, which I'm going to try to draw in the least ugly way possible, which knowing me is virtually impossible. Okay, let me just focus for a second here. Okay, I think I'm going to get this. Please do not break my concentration. Oh yeah, look at that. I shouldn't get cocky. I should wait till it's done. Damn it. I'm really bad at drawing things. Okay. That's not as pretty as the picture in the book, but I think you'll agree that it's about as good as you're going to get out of me. Okay, so there's basically 2 main ways of connecting loads to a three-phase system. So this is what's called the, believe it or not, the Y configuration. Right? It's called the Y configuration because that's how you spell the Y. See, it's in a Y. It's a Y. I don't make this stuff up, people. I just report it. Okay. So this system is sort of has a bunch of applications. And one of the key advantages of this is that when you connect the load up in this way, the neutral is available. So if you have a system and you're trying to ground it, for example, you actually have something to ground onto. So the key advantage of this is that the neutral. So the neutral is available to the load. All right. Now, the other configuration that we could try is called the delta. And this one I definitely need my picture for. So again, A, B, C, and neutral. Oh yeah. Okay. That's called the delta configuration. So just take a look at those for a second. Yes, sir?
Are these work the same way as resistors do, and you convert the 3 and 2 using the equation?
Yes. Yeah. It's same equations. There's some butt ugly equations that let you convert from one to the other, and I don't think we're really going to get into it too much. Okay, turns out it's not that critical. So what's the main difference between the delta and the Y configuration? Right. If you connect up this way, your load has no neutral. Okay, so that would seem like a bad thing, but there's actually some advantages. This one actually turns out to be a little easier for load balancing, and we'll talk more about that probably on Friday. So that's better for load balance. So there's pros and cons, and again, we can sort of talk about in more detail. But there you go. So those are the two basic configurations. We've got a Y configuration, a delta configuration, and the Y configuration has the neutral. The delta does not. So it turns out that you can actually have all different combinations. So you can actually have your sources connected as either a Y or a delta, and you can have your loads connected as a Y or a delta. So there's all these different combinations that you can do, and the book kind of talks about all of them. But we're going to focus for right now on the YY connection. So I guess I'll erase from here, and we'll draw that picture and discuss a little bit how the math works. And then I think we'll have enough on our hands to call it a day. Okay, so let's see here. So let's say this is okay, so this is my neutral. This is my A phase. Actually, let's draw it like this. We'll label this point as point A. So if this is neutral and this is A, this is the A, this is the AN source. And let's say we connect that to an impedance. And we'll connect that impedance back to ground. Okay? So now we're going to do wash, rinse, repeat. Let me just draw this and then I'll ask you some questions about it. Okay, so am I looking at a Y configuration or am I looking at a delta configuration? Right. For both the source and the load? Yeah, absolutely, right? And the one way you can tell is that the neutral is there on both the source side and on the load side. And in both cases, you can see that all three of them have a common point. So that's the common point. The common point is the neutral. So that's a Y configuration for the sources and a Y configuration on the load. So the second thing that we notice is that it's load balanced. So I'm applying the same load to all three. And we're going to talk about right. So we're going to talk about our phase voltages. So we're going to say that again. I'm just introducing lingo. I didn't make this lingo up. So when you express it like this, when you talk about your source voltage versus neutral, the term for that, the term for the magnitude, is the phase voltage. Okay, and we're going to differentiate that in a minute, okay, between some other voltages. Which page am I on? No, seriously, which page am I on? Yeah, here it is. Okay. So for example, I've got a phase voltage for, I mean, it's the same phase voltage, they're just out of phase, but I've got like some amount of voltage on each of my 3 lines. The thing is, though, is that a lot of times when you actually connect something to the, like when you actually connect something to the system, you're not necessarily just connecting it to the neutral. Like you may choose to connect something between the 2 lines. Okay, so sometimes what we worry about is not the actual VA sub n, but we talk about the voltage between the 2 lines. Okay, so let's calculate what that is. So there's this whole other, so we've talked about phase voltages. Those are like your sources. But the other thing we talk about is the line voltages. And the line voltages are basically not the voltage from A to neutral, but rather the voltage from A to B. So we talk about line voltage VAB, which is literally the voltage from A to neutral minus the voltage from B to neutral. All right, do we have a way of calculating what that is? Totally, right? I mean, it's just this minus this. Just 2 complex numbers that I'm subtracting. Should we try that real quick? Right? If I try that, VA sub n is VP angle 0. VB sub n is VP angle minus 120. Do I have the math skills to solve that? Not awful. How can I solve it? I'll give you a hint. Factor out the VP. So I've got VP. What does that turn into? If I factor out VP, what does that turn into? 1 angle 0, which is just 1, minus. Now this turns into 1 angle minus 120. Can I do that? What is that? Get your calculators out. I'm getting mine ready. Right, so this is now 1. So how do I convert that into real and imaginary? Right, so the real part will be the cosine of minus 120. So that's minus a half. And then so then, remember, it's always m angle theta equals m cos theta plus j sine theta. That's the calculation I'm trying to do. But in this case, m is 1 because I factored out the VP. Okay, so it's just cosine of minus 120 gave me that number. Now if I take sine of minus 120, I should get minus root 3 over 2. So minus root 3 over 2j. So I do 1 minus that.
1.0.8.
Yeah, that's root 3 over 2. Yeah. At least it used to be. Root 3 over 2. Yes, it still is. Okay. Okay, so now I can do 1 minus this expression, convert it back to polar. So you got to get good at these numbers, right? Like you can't have this be what screws you up. We'll do this one-time calculation. So now I've got 1.5 plus j root 3 over 2. So let's see, 1.5, enter, root 3 over 2. So I'm going to square both of those terms. I'm going to add them. Holy cow. Okay, so I'm getting VP times root 3 angle 30 degrees. You're not just saying that because that's what's in the book, are you? I got 30 degrees too. Hey, that's pretty slick. Am I out of time? Just about. And we were just having fun. Okay, so let me write this out. So whatever, we did some math, blah, blah, blah. I don't care. I mean, learn how to do the math. But essentially what we've discovered is that if you look at the line voltages, right, the voltage between A and B, you're going to get VL angle 30 degrees. And if you were to do the second line voltage, which was BC, you would get the same magnitude, angle. Any guesses on the angle?
60.
It's always going to be lagging by 120. So if it's 120 degrees back from 30, it'll be at minus 90. Right? If you start from here and go backwards by 120 degrees, you get to minus 90. And finally, the last one, VCA, is the last line voltage. It'll be VL angle minus 210, where VL, we said, was equal to the phase voltage times root 3. And that honk means my time is up. Okay, so there are a bunch of examples in the book, which you should definitely try to do. But basically, what we're trying to do is just build some intuition about converting from line voltages to phase voltages and vice versa. And again, there's not just a magnitude phase. There's not only a magnitude change, but there's also a phase shift, right? So the line voltages are 30 degrees out of phase with the source, with the phase voltages. Okay, we'll pick this up on Friday. We're going to get through it, I promise. And you're going to be glad we did. It's interesting stuff. Thank you.